My name is Hazim Gaber, and today we're going to talk about transmission concepts. Really, we're going to be talking about physics, specifically electromagnetic physics, and we're going to get into the real ugly mathematics. Not mathematics like the heat equation or something, but a little bit of math. So, we've been talking about data. We've been talking about a wire. So let's go back to our copper wire, and we have a transmitter and a receiver. So from our physics idea, now think of this as electricity, and we have a voltage source technically. And we have two. Remember that electricity, it has to flow in a loop. It can't it can't just go down a wire. It has to come back somehow. So on the other side, we have what we call a resistance or a load. So this could be something like a light bulb or a motor or a computer, whatever. So we have electric current known as I, and it's flowing down our wires. And this is positive and this is negative. So the voltage up here is half positive and half negative. And our wire here has a diameter d, and the distance between the two is the distance d. And our load has a resistance r. So this is our idea here. So what we're trying to figure out is how much loss do we have from this load. And all of these items are related. So when we apply a voltage to a circuit with a load, it results in a current. And this was the original idea. But people thought about how much voltage drop happened. And they thought about it and they said, well, if we have a really big fat wire, we have a very low resistance because you have much more space for the electrons to flow. So for a wire that was like this thick, there's so much more space for electrons. There's no traffic jam. Anyway, turns out that we needed some help to try to explain that because what we end up with in reality is we call it an electric field. So it's not enough. What happens is the electrons sit on the surface of the conductor, and so positive charges are attracted to negative charges, and this creates a field between the two conductors. And we call this field becomes known as capacitance. And the field is caused because we've got a positive voltage on top and negative voltage on the bottom. So all of our negatively charged particles are now being attracted to all of our positively charged particles. So they're not just going in circles, they're like basically looking at each other. And so we can measure capacitance in Faradays. And then they figured out that this also made no sense. So now what they think about is that if you have a wire and you have current flowing down the wire, that creates a magnetic field around the wire, which we can call B. So in reality, every wire has a magnetic field caused by the current flowing. And so the bigger the distance D between the two wires, the bigger the field. And this is called inductance. Measured with the H. So if we think about a an electric circuit, we have our voltage and we have some resistance. Eventually we can draw the whole circuit, and eventually we end up at our load because our power line itself has resistance. So we also have a distance here, x. So when we're designing a system, we need to think about R, L, G, and C, or resistance, length, capacitance, and conductance. And these depend on cable shape and then cable properties and then signal frequency. And we're not going to worry about this because it's quite complicated. But we do know that these are all related and we can calculate some of them. So what is important, however, is that we know the impedance of the line. Can measure Z, which is Z is equal to voltage over current. And then attenuation. So attenuation is measured as minus 20 log output voltage over input voltage. This is basically saying signal loss. And then we also have crosstalk, which is whether we have signal bleed from one pair of wires to another. And then we have normal velocity of propagation, i.e. how fast does the signal move down the cable. This is very important. And we can calculate this as V equals C over square root of U E. So velocity is equal to the speed of light and U is the permeability and E is the permittivity. So in any cable, for example, we're measuring V as a percent of the speed of light. And under ideal conditions, could say it's 1, but typically on a data cable, it's between 60% and 70%. And this is important to calibrate your testing equipment because when you're testing for crosstalk and return loss and length, you'll want to program your tester to have the correct propagation speed. So we also have now we call propagation delay. So remember, we had our data cable and it's got 4 pairs, each twisted. So what will happen is over these twists, the number of twists per inch varies from one pair to another. So if you think about it, one with large twists and one with very tight twists, the tight twist cable over the same length will actually be longer. Because if this is 100 meters, and these are practically straight, and these are twisted together tightly, they're going to be much longer to get to the same length. And so if we send a signal here, when we receive it, we'll receive the signal on this pair before we receive it on this pair. And we call that the propagation delay. So we're allowed to have some propagation delay. And there's a formula which is the delay is equal to 534 plus 36 divided by the square root of the frequency. This is measured in megahertz. Sorry, this is not. This is measured in nanoseconds per 100 meters. So this frequency is negative. It's basically seconds to the negative 1/2. Anyway, it's not a dimensionless number, but the delay, it's a very strange formula because the frequency is a square root. So frequency so these numbers must be seconds to the half. I'm an engineer, so I'm trying to think of units. Anyways, we call that the propagation delay. And then the delay between any two pairs is known as the delay skew. So that's the difference between the fastest pair and the slowest pair. And the maximum is 45 nanoseconds at 100 meters. And so the skew is affected by frequency of the transmission and the cable length. And then we also have the reflection, because if we send our signal down the cable and the impedance is a mismatch, part of the signal will be reflected. And there's a reflection coefficient known as P, which is equal to ZT minus Z0 over ZT plus Z0, which we don't have to worry too much about. And then we have return loss, which is very important. So return loss is transmit power over reflected power. So what you want to think about is, remember, if you have a full duplex, you're sending data and then you're receiving data over all the pairs. So each pair is carrying data in both directions. And that means that the source expects its data to bounce back without any loss. So having almost no return loss is very, very good. Now, of course, no system is going to be perfect, but we can measure return loss by saying with the formula negative 10 log P reflected over P transmit. And so if instead of a return, we end up with an echo, or a bounce back, we would have a problem. And then we have S and R, or signal to noise ratio. Oops. So our S and R is negative 20 log V noise over V signal. And we want this to be as low as possible. Because if there's a lot of noise and very poor signal, then we're not going to hear anything. And then we have next or near and cross talk. She mentioned crosstalk. So if we know the crosstalk, we can calculate a bunch of other things with like ACR, or attenuation through crosstalk, and power sum ACR, power sum ACR to or at, near, and at far end, etc. So we have a number of other ways of measuring our performance. So now that we have an idea of some of these measurements, how do we run a test? So say I've installed my data cable and I have my wall jack, and my cable runs up my ceiling and to my server rack patch panel. So I can get a tester like a Fluke DSX. And so I just want to show you some options here. So if we look at a cable tester, our most basic tester will tell us whether we've got continuity on the wires. So that means we know what we call a wire map. Do we have all 8 wires terminated correctly, or are they broken? Now, the fluke, this is actually a basic fluke tester. It'll also tell us the length of our cable, and it'll give us some more ideas about whether our cable is connected to a switch and what kind of bandwidth it's providing. And this is about $1,000. And then if you go to the Versive certifier, so they've built or like a modular system called the Versive, and you can add copper and fiber certifiers, and so they give you a much more advanced idea of crosstalk and other standards. And you cannot just test, Cat5e, Cat6, Cat6a. You can also test proprietary cable like Crestron cable. And then you can even do Cat8 if you have the correct modules. You can do a test in about 8 seconds. And then you have an output. Basically, you run your software, you plug it in, and you get a full chart for each cable. And if you're testing fiber, it can show you where it finds a fault. So now we've said that, we've got our faceplate. Whoops. And we got a tester, and we run our test. Now, you might test this piece, which we call the permanent link, or you might test the patch cord as well. But you may not. Typically, we don't test the patch cords. So there's a TIA standard which lists the performance required. And so a few things that we need to know: the link, the maximum length, is 90 meters plus 10 meters of patch cords. So if our length is too long, then we're already in trouble. Now, technically speaking, even if you exceeded the 90 meters, you could still have a functional link, but you may see a high return loss past 90 meters. You also have to make sure that you've entered the correct propagation delay or velocity into your tester. So there's a minimum insertion loss. There's a maximum. And then there's also next or near and crosstalk. And if the next is too high, you should probably re-terminate the jack. And the fluke tester will tell you which side has a really high next, because remember, it's testing on both ends of the cable. So if it's telling you the main unit is bad, then re-terminate the wall jack. And if it's telling you the far end is bad, the remote, then re-terminate the patch panel port. In all my testing, the links, the biggest reason something fails is because of the next. And I found that re-terminating the jack or replacing the jack in some cases, sometimes you get a bad jack, but re-terminating it solves 99% of the errors. And then we have return loss. Whoops. I hate this mouse. So, where were we? We had length. Max was 90 meters plus 10 meters of patch. And then we had next and 90% re-terminate jack. And we have insertion loss. We have return loss. And a lot of times I find that if we have a return loss, we just reseat the tester. Especially on a high quality cable and jack, sometimes the tester is not seated perfectly in the jack, and that creates a high return loss. The other time I see a high return loss is when we've exceeded the 90 meters, in which case there's nothing you can do about it except shorten the cable. And why do you have a cable that's longer than 90 meters? Well, sometimes you have to run the cable and you don't have a choice, because you may have a building where the only way to get all the cables short enough is to build a second server room, and that might not be cost effective. So technically it's wrong, but the client might say, well, we don't want to spend 50 or 60 or $80,000 to end up getting 6 cables shorter than 300 feet. Whereas right now, they might be 320 feet or 350 feet, and technically they won't perform to the standard, but they'll still function. And so I guess what I'm saying is, with all these codes and regulations, you gotta think about sometimes none of these are legally binding, so there's always a cost benefit analysis. So yeah, those are our main things. Our next, our insertion loss, our length, and our return loss. We also have a thing called power sum, but that's not really um, it's not really part of the standard. It's something we can test for, but nobody tests the patch cords. Although, in reality, when you have a twisted pair, 90 meters, the patch cords should meet the same standard as the permanent link. And usually these patch cords have poor results. So think about type of cable that you're going to use. So we do have now think about this, as we have cat 3, cat 5, cat 5e, cat 6, cat 6a, cat 7, cat 7a, and cat 8. So this is basically phone line 10 meg Ethernet, and this is technically obsolete. Cat 5, which was Ethernet, and 200 meg, also obsolete. And then this is the 3 that are currently in use, gigabit up to. And then Cat 7 and 7A are obsolete because they never caught on. Cat 8 is only used in data centers, short distances, 10 gig. So the performance is 1600, 100, 250, 500, 6A, 600, 7A is 1000, 2000. And then there's a ton of standards that we can look at here as to what we can run on a given cable. Because we call this gigabit Ethernet. We call 10 megabit Ethernet just Ethernet. And 100 meg is called fast Ethernet. This is called 10 gig Ethernet. But the other interesting thing is we can run, you know, a voice 64 kilobits up to 4,000 feet on Cat 3. You know, versus all of these are about 100 meters. And 10 gig, you can only do so some other ideas. Remember, we were talking earlier about our backbone cable. So there's a rule that when I install my backbone cable, so for example, a 25 pair cable between my rooms, I can put 25 phone lines, or I can put 12 data. Oops. I need 2 pairs for Ethernet. So I could put 6 data, no Ethernet. Or I could put 12 because gigabit. Or I could put 4 pairs. I could put 2 pairs fast Ethernet. End up with 12 data. Depends on how I've terminated my cable. Or I could run, here's a little hack. So I have a Cat 6 cable and it's got 4 pairs. If I'm only using 2 pairs, I can use 2 pairs for our data, and I can use third pair for a phone, and the fourth pair for a phone. And this will only run at 100 megs. But sometimes we do this when we only have one cable. So I have a cable that's feeding a photocopier, and I need to run Ethernet to the photocopier and a fax. But I've only got one cable, so kind of split it. It's not recommended, but it can be done. There's a rule though. There's a few rules that ANSI came up with and said no more max of 12, 10 meg per second Ethernet. In one cable. And do not combine signals with different power levels. Do not mix balanced and unbalanced signals. And we've got another idea now. We call them media converters. So I might have a coax that I want to convert so that I can match the impedance. So we got a device called a balloon. And a balloon takes an impedance from a twisted pair and allows us to run a coax. So if I have a security camera that runs a coax, I can put a balloon here. I can run Cat6 to the camera. I can put another balloon, and I can put coax back to the DVR. We can also use a signal converter to filter or amplify our signal, convert analog to digital or digital to analog. And then the other idea is PoE, which is power over Ethernet, which is quite complicated. So the details are, say I have an office. I might have a wireless access point, IP phone, IP camera, and each of these needs Ethernet, and it needs power. Ethernet plus power. So I have to put a power outlet next to each device, which is quite expensive. So what if I could bring the power over the Ethernet? And the way we do that is we get a PoE switch, and the PoE switch sends power, or we can use a power injector. The PoE switches are expensive. So if I've only got one or two devices, say I got one Wi-Fi access point in the office, then we put a PoE injector and then our switch. And this gets power from an outlet, and it injects power into the data line. And the WAP doesn't know the difference if the power is coming from the PoE injector or if it's coming from the PoE switch. Now, obviously, there's a lot of advantages here because we don't need power outlets. And then we can have installation without an electrician or a permit. We can also remotely reboot the device because we can toggle the power from the switch port instead of having to physically go unplug it if it crashes. So say my camera stops responding, I don't have to send a tech out to manually power cycle the camera. I can just do it from the switch. So remember that we have our wire, we have our cable with 8 wires. And when these are terminated to a jack, there's 8 pins. So there's a bunch of different PoE standards. And the original one was 802.3 AF, which was 15.4 watts. And then 802.3 AT, which is 30 watts. And now 802.3 BT, which is known as type 1, type 2. Now I have 60 watts or 90 watts. So remember, we have 8 pins, 8 wires in our cable, and we use wires for 10 meg Ethernet and 100 meg Ethernet. We only use pins 1, 2, 3, and 6. So type 1 and type 2 use pins 4 and 5 or 7 and 8 to deliver power. Or can use 1 and 2 and 3 and 6. Now 3 and 4, however, use all 4 pins to send power. Because if we used only 2 pins or 4 pins, we'd we'd overheat the wires. Now technically, the receiving device and the switch, when they first connect, the switch detects that the device needs power, and then they negotiate a power amount. I should mention, I said earlier, WAPs and IP phones and IP cameras. I mean, the list goes on now. We can have thin clients and have LED lights and have building automation, point of sale, because devices are becoming much more energy efficient, and so and the power rate now at 90 watts, you can do a lot with 90 watts. So yeah, we have a lot of different devices that can be powered. But when the device first connects to the switch, they negotiate a power amount. And now we have something called dual signature. So what happens is we can send two separate power supplies, two separate power amounts. So say pins 1, 2, 3, 6, and 4, 5, 7, 8. So each set of pins gets a different current and voltage. And why that is because maybe they have a wireless access point which has, for example, a antenna and a controller. And the controller needs one type of power and the antenna needs another type of power. So now the circuitry in the WAP can send a different type of power to the controller, a different type of power to the antenna. We don't have to design a transformer inside the WAP. So WAP's cheaper and um, lighter. So what I want you to think about is when we started, we had link, layer, discovery, protocol. So what happens is a device first boots up, talks to the switch. And this is a type 3/type 4 technology, but compatible with type 1 and 2. And so these two devices negotiate the power requirements. And we can even daisy chain a second device to the first one, which is pretty useful, say, for LED lighting. So a negotiation is important because, say, we have a 48 port switch. That means at 90 watts times 48, that's 4,320 watts. So the switch may not have the capacity to support that much power. So if it's sending 90 watts to the first device and 90 watts to the second, etc., etc., it's going to run out of power. So what we can do is negotiate. So maybe this guy only needs 60 watts, or maybe 30 watts. And this way, our switch only sends out the power that it needs, and it can save the rest of the power for another device. So that concludes copper transmission. And so next we're going to look at fiber optic cable. Any questions?